All right, welcome back. So now we're going to continue where we left off. So in the previous part of the lesson, we had finished talking about the directional derivative. And so let's just kind of resume. Yet another way to write the formula. Remember that if we have a unit vector with components u1 and u2, which is what we use in the previous formula, you could also write u in terms of the trig functions. Right? If it's a unit vector, then the x and y components are simply going to be the cosine and the sine of the angle. So if this is u, right, this is just going to, and remember that the magnitude for the unit vector is 1. So this has to be cosine theta here, and this has to be sine theta for the vertical component. And so you could also write the unit vector this way. And so for that reason, we have that the directional derivative in the direction of u of f of x naught y naught is going to be partial x evaluated at x naught y naught. And then instead of u1, we're just going to use cosine theta plus partial y evaluated at the point times sine of theta. Okay, so another formula. And depending on what's given to you, I mean, that's pretty much what dictates which one to use. All right, so we'll go through a couple of quick examples here. So let's just do a pretty standard one. Let's find the directional derivative at 1, 2 for the function f of xy equals 4 minus x squared minus 1/4 y squared in the direction of a unit vector that makes a 60-degree angle with the positive x-axis. And so, again, you can just utilize the formula that we just talked about, right? If we have a 60-degree angle, then we know that the unit vector is just going to be the cosine of 60 and the sine of 60. And so that's just going to be 1/2 root 3 over 2. And so now when we're finding the directional derivative, we also need partial x. So if we go back to f of xy, partial x is just going to be negative 2x, and that's it. Partial y will be negative 1/2 y. And so the directional derivative at the point 1, 2 will be partial derivative with respect to x times the cosine of 60, which we had as 1/2. And whoops, I wrote that I was plugging in 1 and 2, and I didn't plug in 1. All right, so that should be negative 2 times 1. And then minus 1/2 y is going to be 2. And then we still have the sine of 60, which is root 3 over 2. And so if you clean that up, you get negative 1 minus root 3 over 2. Okay. Next example. find directional derivative of f of xy equal to x squared sine of 2y at the point 1 pi over 2 in the direction of v equals, let's just go 3, 4. Okay. So again, the key is to use the nice formula that we derived yesterday, thanks to the chain rule. You want to always have a unit vector. So if we have an angle, that's easy. You just do the cosine and the sine of the angle. If we have a normal vector like this one, then you first have to find the magnitude, right? And so that'll just be the square root of 3 squared plus 4 squared. Magnitude is just going to be 5. And so that means that when we divide the components by 5, our unit vector will be 3/5 and 4/5. All right, so first we got to find the unit vector. There it is. And of course, just like in the previous example, we're going to need our partial derivatives with respect to x and y. So if we go back up here, partial derivative with respect to x would just be 2x sine 2y. And with respect to y, we're going to do x squared, and then sine becomes cosine 2y, and then don't forget we got to do the chain rule here, so the derivative of 2y is going to be 2, so we pull that 2 out in front. And so now the directional derivative of f of xy at the point 1 pi over 2, just plug it in. So we're going to do partial x, so that'll be 2, plug in the 1, and then sine of 2 times y, so 2 times pi over 2, plus partial y, so that'll be 2, 1 squared, cosine, and again 2y, so that'll be 2 times pi over 2. And if we go ahead and figure that out, this is just going to be pi, the sign of pi there. That's just going to be 0, right? So we can cancel that out. And then here we have, what, 2 cosine of pi. The cosine of pi, oh, I'm sorry, I totally forgot. It's kind of a big deal. So we have partial x, and then don't forget we need these guys, right? We need 3/5 over here, and then we got to multiply this by 4/5. Hopefully you saw that and were wondering what the heck I was doing. Anyway, first term still cancels out because we get 0 there. And now here we're left with 2 times the cosine of pi times 4/5 cosine of pi. It's just going to be -1. And so here we get -8/5 for our answer. Okay. So directional derivatives, done. Now we're going to go on and talk about gradients. So what is the gradient vector? And so here's the definition. If f is a function of x and y, then the gradient of f is, and then we use the symbol del. Okay. So upside down triangle, that's what we call del. So if you see this symbol in front of f of xy, it means that we are doing the gradient of f of xy. And the definition is going to be the vector And it's pretty easy. It's just going to be the partial derivatives with respect to x, and then partial derivative with respect to y. And so here's the definition for the gradient. You get a new vector. The first component is the partial derivative with respect to x. The second component is the partial derivative with respect to y. And then obviously in 3 dimensions, similar, right? The gradient of f of x, y, z, that's just going to be, and I'll just go short notation here, partial x, partial y, partial z. Okay. So now we're not just doing this for this reason, but it's an important one to note here. Since we know that the directional derivative is equal to partial x times u1 plus partial y times u2, okay, I hope you see that this looks suspiciously like a dot product, right? Here, whoop, too much. But if we highlight it this way, you can see that we have 2 vectors that were dotted, right? The first vector would be partial x comma partial y. Lo and behold, that is this one up here. The second vector is just u1 and u2, so that would just be your unit vector u, right? And so we can now say that the directional derivative is going to equal the dot product of the gradient evaluated at the point with the unit vector. So yet another way to interpret the directional derivative. Okay. So let's go ahead and just do a quick example. Go ahead and find the gradient of f if f of x, y, z, or actually just f of x, y, is equal to y natural log of x plus x, y squared at the point 1, 2. Okay, so let's find the gradient. And it's just using the definition that we discussed up here, right? You do partial x for the first component. So that's just going to be y over x. Natural log of x is 1 over x times y. You get y over x. And then here the derivative of x is just going to be 1, but we still got the y squared. So there's the first component. Second component, you take the derivative of f with respect to y. So that just gives you natural log of x plus 2xy. And so now at the point 1, 2, plug it all in there. and again, I want to remind you, when we're doing examples, feel free to pause the video, work through it on your own first, and then, see if you're getting the right answers. That's a good way to check for understanding. Right now I'm just trying to get through all the material here as quickly as possible, so I'm not really stopping since there's no class in front of me. I'm just recording this outside of class. So take that responsibility on your own and try some of these if you know what's going on. Anyway, so if you plug in 1 and 2, you're going to get 2 over 1 plus 2 squared, which is 4, comma, natural log of 1 plus 2 times 1 times 2. 2 plus 4 is 6. Natural log of 1 is 0. So then we just get 4 for the second component. All right, so pretty straightforward. And now let's go ahead and get into some properties of the gradient. And so we'll just kind of outline both of them. Okay, first one. At the point xy, the surface z equals f of xy has its maximum slope. In other words, if you have some surface here's x comma y, and here's a point, right? And so maybe this green line indicates the steepest slope possible, right? Remember that we have an infinite amount of directions that we can go in, and so what we're going to say here is that the maximum slope is always going to be in the direction of the gradient of f of xy. And the max slope is just going to be the magnitude of the gradient vector. Okay, and then similarly, min slope is just in the opposite direction and it's just the opposite of the magnitude. Oh, rewrite that. Is the opposite of the magnitude of the gradient of f of xy. Okay, and if I had more time, I would spend a few extra minutes here going through the proof, but I can outline it for you. Okay. Remember that the directional derivative is just essentially the dot product of the gradient and a unit vector. And so remember that a dot product can also be written, so I guess I can just outline it here. So here's a quick abbreviated explanation. We know that the directional derivative is the dot product of the gradient of f with u. Okay. We also know that if we have a dot product, that we can write the dot product as the magnitude of f times the magnitude of u times the cosine of the angle between these two vectors. And since this is the only thing that's going to affect how large this is, right? This is just going to be equal 1 because it's a unit vector. So all that's left is the magnitude of the gradient of f, okay? And cosine of theta is at a max when theta is 0, right? Because that's when the cosine is 1. And so that means that we are in the same exact direction as the gradient. And it's at a min when theta is 180 or pi. So that means the exact opposite direction. Okay? And here's the value of the directional derivative. Okay, I know that was kind of quick, but hopefully that shed some light as to why. Okay? And then let's just add one more property here, and then we'll get to some examples. If the gradient of f is the 0 vector at P, at a point, then all directional derivatives of f at P are 0. Oh, just making sure my computer didn't stop recording. Okay. All right, so those are the three main properties that we got to know. And now So just, you need to make sure you know that, right? We will get to an example where we utilize this, but we do want to talk just briefly about some contour plots. And before that, let's get through this theorem real quick. Let's go ahead and assume that f of xy has continuous first order partials. In an open disk centered at a point x naught, y naught. And that the gradient, so obviously if the first order partials exist, that means the gradient exists. And let's also assume that the gradient of f does not equal the zero vector. Then what we have is that the gradient of f is going to be normal to the level curves or surfaces, depending on how many dimensions we're looking at, but normal to the level curves of f of xy through the point x naught, y naught. Okay. Now, here's an example to kind of illustrate what we're talking about. So let's say we have a contour plot here. And let's say we have several level curves. Let's say that this one has a height of 0. Let's say this one has a height of 5. Let's say this is a height of 10. Let's go one further, 15. Kind of ignore that little dot there. Okay, so let's say here are a set of level curves for our surface, and let's have a few different points. Okay, so we have, let's say this is P, let's say Q is over here, let's say R is over there. Okay, so I hope it makes some intuitive sense, right? That we don't see the entire contour plot, but you can kind of gather that somewhere over here, it looks like we might have a max, right? Because it looks like if we head towards this direction, that we have maybe a maximum point somewhere around here. And now keep in mind, let's tie that together with the gradient vector. The gradient vectors are always going to be pointing in the direction of sharpest increase, right? And so that's going to be, if I actually draw those in, so the gradient vector at P would be kind of pointing that way, right? It's going to be normal to this level curve. The gradient vector for Q, same idea here, pointing this way. Okay, and then the gradient vector for R, same idea, pointing that way, making 90-degree angles with their level curves. Okay. Now, so you just have to know that that's visually kind of what's going on, right? And so if you're standing at point P and you want to get the sharpest increase, you're going to just follow these level curves, go normal, so this way, and then maybe that way, and you can kind of eventually see there's a path. You can connect all this to make a path that leads you to that maximum, right? And so that's one thing. The second thing is you should be able to look at a contour plot like this, and if I ask which point has the largest slope, or yeah, that's good enough. Which point has the largest slope just by looking at this, right? So all you have to do is pay attention to the level curves, right? If you're standing at Q and you're going this way, you're going to travel more distance to increase a height of 5. Here, it looks like it's a little less, right? Because all of these level curves are 5 units up on the Z scale. But if you look at R, to get 5 units higher from where you currently are, so if it looks like right now, if at R you're at a level of 10 units, to get to 15, you don't have to travel very far, okay? And so the closer the contour lines are together, the closer these level curves are together, then the steeper the slope that you're going to have. And so I hope it's clear, okay, that R is the winner there because the level curves are closer together at that point. All right, let's keep this rolling. And so we're going to try to tie the two concepts I gave together. One, well, let's just kind of go through it first. So here's another example. Let's say the temperature on a plate, the temperature on a plate can be given by this function, 20 minus 4x squared minus y squared. So this represents temperature on a plate. And x and y are both in centimeters. So the question is, in what direction does the temperature increase most rapidly? And what is the rate of increase? Okay, so we have a plate, and the temperature on the surface of the plate is modeled by this. And so if we're looking for the direction in which the rate of change is the fastest or the biggest, all that means is really we're finding the steepest slope. And to do that, we got to find the gradient, right? So let's find the gradient of t. The gradient of t, if I'm looking at this function, will just be minus 8x and minus 2y. And now if we evaluate the gradient of t, oh, I need to give you a point, sorry. In what direction from the point to negative 3? So we're standing at this location, and we want to know towards what direction should I move to get the sharpest rate of increase. Sorry, I left that out. Okay, so we take our gradient. We know where we're standing, which is at 2, negative 3, so we're going to plug that in. And so you're just going to get negative 16, 6. Okay, so this is the direction that you travel in, right? So from 2, negative 3, you'd go 16 left, 6 up. So kind of in this direction, that would be the way to go, right? If you connect those and make that vector. And then the magnitude, the rate of increase, you just take the magnitude of that vector. That's just going to be the square root of square both of those, 256 plus 36. I do have an approximation. And let's get some units in here. That's why I gave you all these units, right? So we're going to go 17.09 degrees per centimeter. All right. And now finally, so this is what I was trying to illustrate. So this gives you which way to travel at this location. And so we determined that, okay, we're going to kind of go this way. It does not mean, however, that you're always going to be traveling along this line. Because as you move, right, the sharpest slope might change the direction. And so you're going to maybe have a curve to follow. All right. And so that's actually kind of how heat-seeking particles or heat-seeking missiles work, right? They chase the hottest temperature, and so they're always looking for um, the sharpest increase in the rate of change. And so, again, if it's straight ahead, then you're going to see that we're going to go that way. But depending on what's going on, you might have a curve for that path. And so let's do one more example tying all this together. So let's say we have a heat-seeking particle that moves in the direction of the max increase. And we want to find the path. So what is the curve or the path of the particle? And let's just use t of xy from the previous example. So if we're modeling the same temperature and we have a heat-seeking particle that's always going to be chasing that, what's the path going to look like? All right, so here's the solution. So first we start by saying, okay, I don't know the path. Let's call the path r of t. Now I know that if I take the derivative, that's going to be dx dt and dy dt. We also know, since this is the velocity vector, that the velocity vector and the gradient must be in the same direction. Right? Because if we're chasing the max increase, right, then this is the vector that dictates that, but we're always going to be following the gradient of the function from t. And so what we can say now is that v of t has to equal some multiple, right, if they're in the same direction, some multiple of the gradient of t. And so if that's the case, now we have dx dt, comma, dy dt. I'm just plugging in the values here. And over on this side, remember we found the gradient earlier. It was negative 8x, negative 2y, but now we have a constant in there. And so that's going to be minus 8kx and minus 2ky. Okay, so far that's what I know. And from there, I can then kind of go component by component. I could then say, okay, well then that means dx dt has to equal minus 8kx. I also know that dy dt has to equal minus 2ky. Now, if I kind of separate variables for each one, and so let's move the x's over here. So I'd get dx, negative dx over 8. That's going to equal k dt. Oh. Do the same thing here. Negative dy over 2y, that's going to equal k dt. Since when we separate variables for each one of these, now we get that these two have to be the same, right? These two have to be the same. So let's write that out. Minus dx over 8x has to equal minus dy over 2y. And let's clean things up a little bit. I'm going to multiply by 2, negative 2. And so now I get dx over 4x that's going to equal dy over y. Okay, and we have our variables already separated. Okay, so we can now integrate both sides. And here I get 1/4 times the natural log of x. And that's going to equal natural log the absolute value of y. And we do have some constant from the integration. We can just put that together on one of the two sides. And now if I exponentiate both sides, and sorry, I'm running out of time here, so I'm going to go quickly. I'm going to put this in here. We're going to get x to the 1/4. This is just going to become y. And then, so this becomes y times e to the c, basically. We can just recreate a new constant where c is going to equal, big C is going to equal e to the little c. Okay. And so now we essentially have our equation here. Maybe I can move this constant over. Let's call it, oh, doesn't matter. Let's go 1 over c, x to the 1/4 equals y. And so this is just another constant. Let's call this c1. So now we have c1 x to the 1/4 equals y. And so this is the path. This is the path of the particle. Okay. Now we can go ahead and find this constant since we knew that we were starting at 2, -3, right? If I plug those conditions in, we get -3, well here, c1, x is 2 to the 1/4, that has to equal -3. And so my constant is going to be -3 over 2 to the 1/4. And so my final answer is going to be -3 over 2 to the 1/4 times x to the 1/4. And so this would be the path based on the condition that's given to you. All right, sorry for hurrying through there, but 0 hours just started and I'm late to meet with a student. So if there's any questions, we can certainly go over some of these questions in class. All right, have a good day.